Hey everybody, I wanted to talk to you in this video about hypothesis testing. Hypothesis testing is a really important process that we're going to be spending a lot of time on for the rest of the semester. So I want to make sure that we are good and solid on it. We're going to spend a couple of weeks doing it, doing just the basics. And then we're going to talk about some specific hypothesis tests. And then the third test, all the material after the second test, is all hypothesis testing, basically with some linear regression. It's maybe a quarter of the material is linear regression, something like that. So let's get started on hypothesis testing. So the idea of hypothesis testing is this. We're going to make a decision. This is our statistical way of making a decision, essentially. So the basic idea is this. We're going to decide between two competing ideas, the hypotheses, two competing hypotheses. One of them called the null hypothesis, and then the other one called the alternative hypothesis. And the thing you really want to remember about which one is which is that the null hypothesis is the default. That's the thing that if you don't see anything unusual in your data, that's the thing you're going to believe is the null hypothesis. It's only if you see significant evidence of deviation from what you would expect that you're going to believe the alternative hypothesis. That's the basic idea. What we're going to do is we're going to have a null hypothesis of here's a statement of our default, and then the alternative hypothesis is going to be the opposite of that, which we'll talk about in just a second. And then we're going to gather some data and try to determine which one we think is right, basically. With the sort of burden of proof being put on the alternative hypothesis, right? The null hypothesis is going to be, this is the thing that seems the most reasonable given an absence of other information. So that's the basic idea. So here we go. The thing I said is basically in here. One of the things that I'll point out is we're going to write these in terms of equations. Or inequalities, I should say. And so the null hypothesis is the one that gets the equal sign, and the alternative hypothesis never has an equal sign. Now, I'll explain why significantly later, probably a couple of videos from now. It's necessary for the math, but that is a thing that you want to keep in mind, is that null hypothesis gets equals, alternative hypothesis does not. And again, null hypothesis is the default. Alternative hypothesis is if we see something weird, or when weird is not exactly the right word, if we see strong evidence that our default is wrong, basically, is when we choose the alternative. One thing I do want to point out, they must be mutually exclusive. You cannot have an alternative hypothesis and a null hypothesis that can be true at the same time. That's not okay. We're eventually going to decide we think this one is true and that one is false. And so you can't have it where they're both true, because then you can't make your decision. So you always want to phrase your hypotheses in such a way that one of them must be true and the other one doesn't have, or the other one can't be, regardless of which way the data points you, right? It can only ever be one of them true. You've probably seen this phrase before at some point, I would imagine, and maybe not, I don't know. Statistically significant just means we accepted the alternative hypothesis. We think that the alternative hypothesis is true. The reason we call it significant is that we need to see a significant deviation from what we would expect out of the null hypothesis to make us think that the alternative is true. And so we would call that statistically significant. It's just the phrase for it. Very often you'll just hear it referred to as significant. And if you hear significant, it means statistically significant in a statistics class in general. Okay, so here's my first example. We're gonna write some hypotheses. They're pretty straightforward here. So we got Janet. She works in R&D, and she's at a company that makes frying pans. The pans they make now last an average of 7 years. And Janet thinks she's got an idea that will help them last longer. And so to test her idea, she's going to do a hypothesis test. So the null hypothesis is the sort of wet blanket default hypothesis. Your null hypothesis very often says something to the effect of, that thing that you tried didn't work, or whatever idea you have was not correct. It's actually the way it's always been, right? That's sort of your null hypothesis. And then the alternative hypothesis is often the thing that the person doing the research actually thinks is true, but needs to gather evidence to prove, which is what you're doing with a statistical test. And I actually shouldn't say prove, gather support for, because as always, we're only dealing with samples. And so nothing is 100% certain in statistics. You want to stay away from words like prove, like I just mistakenly said. So yeah, not prove, but gather support for. That's really what we're trying to do here. All right, so the null hypothesis here is that thing that Janet tried didn't work, and her new pans are the same as the old pans, right? Given no new information, that's your good starting point, right? Your default. Unless we see something significantly different than this, we're just going to continue to believe the pans still have average lifespan of 7 years. And the alternative hypothesis is the opposite of that. It's the thing that Janet believes, right? The average lifetime of a pan made with new material is more than 7 years, right? It got better. So null hypothesis, same, everything's the same as always. Alternative hypothesis, things are different, right? And so the things are different hypothesis is the one that we have to gather evidence to defend, right? That's the thing that we really need to say. We really need to show that this is true, as opposed to just believing it, right? So absent other evidence, we're just going to continue believing the pan's lifetime is 7 years. If we have significant evidence, then we'll think it's longer. You can also write these like this. And this is, in fact, how we'll write them most of the time. I just wanted to do it in words to sort of get that idea in your head that these things represent words and they represent ideas, right? And so here is my null hypothesis. The mean is less than or equal to 7, and the alternative is the mean is greater than 7. Now, there's actually a lot of information packed in here for in a couple of ways. The thing you want to see here, mu, this is talking about the population mean. So this means we have to identify this mu after reading this as the mean lifetime of these pans, or of the new pans, is 7 years or less, right? And that's, you have to incorporate all those ideas into your head at the same time, right? The mu is not just, you don't want to think of it as just mu, as just some random letter that we're using. It really means the mean lifetime of these pans made with the new material is 7 years or less. And that's the way you want to think of it. It's just shorthand to write it as a mu, but you want to think of it in terms of the idea that it's trying to convey. Another thing that's easy to mess up is that this mu and this mu are both referring to the same population mean, and they're both about the new material. It's very easy to think that, oh, this one's about the new material and that one's about the old material. No, not at all. They have to be about the same thing, and they have to be contradictory, because we can't have a case where, like, oh, the new material lasts longer than 7 years, but the old material is less than or equal to 7 years, because those two things can both be true, right? And we can't have that. We're going to say we think this one is true and that one is false, and so they have to contradict each other, because otherwise you don't get a choice like that. So be careful when you're writing these. A couple of things I want to point out. This must be a parameter of some kind. That's not going to be a statistic. This would definitely not be X bar, because X bar is a thing that we know, right? We don't have to hypothesize about the value of X bar. We know X bar. It's in the study that we did. The thing we are hypothesizing about is what the population mean is, not the sample mean. That's true for every parameter. Every hypothesis test you ever do will be about some parameter. There will never be one about a statistic. We are going to use a statistic, but we're going to use it as our representative of the parameter, essentially. So hit a couple bullet points here. So these mu's refer to the new material only. Can't have new and old. It's got to be about the same thing. These two things have to contradict each other, and they're about parameters. It's always true. Okay. When you write hypotheses, they basically come in 3 forms. Later on, we'll learn some different ways to write these, but for the hypothesis tests that we're doing right now, they basically come in 3 forms. some parameters less than or equal to a number versus some parameters bigger than a number. Same thing with just the other way around, right? So I honestly like to think of these in terms of the alternative hypothesis, because the alternative hypothesis is usually the thing that you think is true, or the thing that the researcher thinks is true, and then the null is just the opposite of that, right? That's usually how we end up, or how I find it easiest to write these. So for instance, up here, we think that or Janet thinks that the mean lifetime of pans made with new material is more than 7 years. That's the thing that she's been working on, and she thinks it's true. The alternative, or the null hypothesis, is just not that. So she's doing this, right? Parameter mu is greater than 7 years, and then once you've got that down, then you just say, okay, well the null is just the opposite of that. You could certainly write these, you'd be asking a different question to write them in a different way, right? So if she wants to test this hypothesis that mu is less than 7, that the mean lifetime of some set of pans is less than 7 years, well, and the alternative is just the opposite of that. If she wanted to test the hypothesis that the mean lifetimes of these pans is not 7 years, but doesn't know which direction she thinks it's going to go, then not equal to. And then the opposite, or then the null is equal to. A thing I do want to point out here, this is always fine. You can always just stick an equal sign in the null hypothesis, even though that doesn't actually cover all the options. It turns out that kind of doesn't matter. What we're really saying, what we're really thinking about is this thing true, right? And so we don't really care what the symbol here is. When we, all right, let me tell you a little bit about the logic that we're going to be using when we eventually make our choices, and why we don't care about the sign there. The logic that we're going to be using goes something like this. We're going to be deciding if we have enough evidence to reject the null hypothesis, right? And if we do have enough evidence to reject the null hypothesis, that's basically the same thing as saying that we think the alternative is true. Sometimes we won't get enough evidence to reject the null hypothesis, in which case that we will think that the null is true. The reason we don't care about the sign is we're really trying to address questions like this, right? Average lifetime of pan made with new materials longer than 7 years. And if we don't see enough evidence for that, then we sort of don't care what symbol is in the null hypothesis, because we just think this is not true. Or we don't have enough evidence to say that this is true, so we just go back to our default. So it sort of doesn't matter whether it says less than or equal to, or just equal to. And as I'll explain mathematically in a couple of videos, it turns out we don't use the less than part of it. We only use the equal to part of it. So I feel like that explanation didn't clear things up very well. I will encourage you to read your book. The authors have I don't remember what page it's on. They have a little discussion about how one of the authors of your book just uses equals all the time in the null hypothesis, and the other one specifically tries to go greater than or less than, to be the opposite of whatever this is. When I learned to do it, I originally just did it with equals everywhere. I try to do it more like this now to help convey the idea of less than or the pan lasts no more than 7 years, but mathematically you could just write this as equal to, and it would work just fine. Yeah, this statement about I tend to use equals all the time is kind of true. I sort of default to that, but I will try to write it in such a way that it reflects the actual idea I want to convey. And I think you should too, but I won't mark you down either way. Okay, so let's do a quick question here, a quick example. So car company executive wants to find the total cost of owning various competing cars, including purchase price, maintenance, and gas, to compare them to her company's car. Now, she knows what her company's car costs. Her company's car has an average lifetime cost of this per year. I want to write hypotheses to test whether the competing cars have the same average lifetime cost as her company's car or not. So I'm going to do it like this. So I'm going to start by writing null hypothesis. Oh, and by the way, if you want to write subscripts and superscripts to make them look more professional, there's buttons in Word for that. There's buttons if you, in whatever program you're using, there will be some subscript or superscript button. I tend to use the keyboard shortcuts. So this is just control equals to get 0, H0. Null hypothesis is that the mean cost of her company's car, and that'll be a mu in a second. I'll change it in just a second. We're not interested in hypothesizing about the mean cost of her company's car. We know what that is, right? They've done, thousands of hours of research on it. We're pretty confident that her company's car costs $5,150. We want to know if the competing cars have the same average lifetime cost as her company's car or not. Well, her company's car's average lifetime cost is $5,150 a year. So we want to see if the mean is $5,150 or not. This is a mu here. All right, so there is my null hypothesis, is that the mean price is the same, or the mean average lifetime cost is the same. And then when you write hypotheses, the way you really want to think about it is pretty much everything should be the same except the symbol should change, right? And so if I'm testing to see whether the competing cars have the same average lifetime cost as her company's car or not, that just means not equal to. Right? So that's what I want to put in here. Sorry, my Zoom stuff is interfering. Symbol and what not equal. So there you go. That's it. That's what the hypotheses here look like. Null hypothesis, everything is the same. Alternative hypothesis, no, it's not. Oh, I wrote that as a 0. Sorry, that's a 9. There we go. That's it. That's all there is to writing these. And I'll say this, writing hypotheses tends to be pretty simple, but you do have to be really good at it because we're going to do it a ton. And if you mess this up, it ruins your whole problem. So another one. So we don't have to do this with just means. We can do qualitative data as well, like this person. Sam was a political pollster, finds information online that claims that 60.21% of voters in Santa Barbara are registered as Democrats, which seems high to him because Santa Barbara is very rich and rich people tend to be conservative. And so he wants to do his own test, see if that percentage is too high, using the following hypotheses. So the way you want to think of this is, absent other information, Sam will think that the online thing that the thing he read online is probably right. Those people probably did a poll. He thinks that poll might be off, but he's just going to check to see if that's right. So absent other information, he's going to believe the poll or believe the thing he read. And then if there is significant information to the contrary, then he will think that the poll wasn't right. So, yeah, so I would probably write these hypotheses like this or with percentages. But notice that we are writing not about a population mean, but about a population proportion, right? P, population proportion. So here, this P stands for the proportion of all Santa Barbara registered voters who are registered as Democrats, right? So that P contains a lot of information in it. And we think that's, 60.21%. Unless we have some reason to believe otherwise. And then if we have a reason to believe otherwise, we can think that it's less than if that's what we get. All right. Yeah, that's kind of all I want to say about that. Do note that these are contradictory. Like, if this is true, then that's not. And if this is true, then that's not. And it has to be that way. All right, so we've got some examples to do here. Tire company claims their tires last an average of at least 85,000 miles. You want to check to see if that claim is true. So we're going to write some hypotheses. So to check to see if that is true, absent other information, we will go ahead and believe them, right? Unless we have strongly contradicting information, we'll believe their claim. So let's see here. Mu. So first thing I want to notice is that this is going to be a question about mu, right? It's quantitative data right? The number of miles their tires last. So this mu represents the average number of miles that their tires last. Right? And they're saying that they last an average of at least 85,000, so that much or more. What did I do? I messed something up. Oh, I did equation instead of symbol, didn't I? Yeah, my bad. All right, so they are saying that the mean is at least 85,000 miles. I did too many numbers there. Oh my gosh. There we go. And then the alternative hypothesis would be not that the mean is less than 85,000 miles. Right, and that's all we have to write. Mean is less than 85,000 miles. There we go. Those are the hypotheses that I want for this. All right. Lauren here reads that the average height of all giraffes is 15.5 feet. She thinks that is too short. So she's been on safari in Africa and she wants to do a hypothesis test to see if the average heights of giraffes is more than 15.5 feet. So she is testing to see if the height is more than 15.5 feet, but absent evidence that pointing in that direction, she will believe the thing that she read previously, right? So this is still quantitative data because this is still, I'm going to go grab these and copy them because this is still, these are numbers, right? Height is quantitative. So her alternative hypothesis, she thinks that giraffe height is more than 15.5 feet. So that's what we're going to write for the alternative hypothesis. And then the null hypothesis is the opposite of that, less than or equal to 15.5. Now it would be totally fine to write this as equals, right? That's okay. That's actually what it says in the problem. So maybe I should write it that way since that's what it actually says in the problem. Math is going to work out the same either way. All right, you read a study online, claims the percentage of Americans with blue eyes is 26%. That study is 30 years old, and you're curious if it's still true. So we want to write hypotheses to test whether the percentage of Americans with blue eyes is 26% or not. The or not should be a big clue. This is going to be a not equal to alternative hypothesis. And in fact, that is true. We want to check to see if something is true or not. And so either direction, either above or below, will cause us to think that it's not true. The parameter we're using here is not mu, though. The parameter we're using is p, because we are testing to see if something is true about a proportion or percentage. So we have to make sure we're using the right one there. And then obviously the opposite of not equal to is equal to. And 85,000 is not the number I want. What am I comparing it to? 26%. Oop. Let's try to get that right. There we go. And that's it. All right. So when you are writing hypotheses for your hypothesis test, what you're trying to do is capture the idea that you are checking in your hypotheses. Almost always, the thing that the researcher thinks is true will be the alternative hypothesis. Sometimes the researcher has no obvious investiture in the outcome, in which case you have to read from context to figure out what's going on there. But in general, the thing that you're testing is going to end up in the alternative hypothesis, and then the null hypothesis is just not that, just whatever the opposite of the alternative is. All right. I want to explain what we're doing, like how this works basically, which we'll do right here. And then I think I'll end the video there. Yeah. This is a good place to end it. All right. So here's the basic idea. Basic idea goes like this for every hypothesis test. I should maybe not have put right hypotheses here first. This is figure out what you're trying to test, right? Figure out formulate a question essentially, and then turn that into hypotheses and right hypotheses. After you have done that, then you gather your sample. Notice that you never want to gather your data first before you make your hypotheses, for a variety of reasons. We're not going to go into them too much in this class, but just be aware that if you like have a rooting interest in the way this comes out, gathering your data first can lead to a lot of biases. So, or gathering your data and then writing your hypotheses can lead to a lot of biases in the way you write them, and you don't want to do that. So to make your hypotheses as independent as possible, you just write down what you're trying to test, and then you go gather your data. Now, for us, this is just going to be like read out of the book. And then the question that we ask basically is this: if the null hypothesis is true, then this sample that we just gathered would be really unusual or not that unusual. And we'll talk about what this means in the next video, or maybe 2 videos from now. But that's basically the question we're asking. If we think about the null hypothesis as true, then is that thing that we saw like crazy and weird? Then we should probably reject the null hypothesis, right? Because if something very unusual happened under the assumption that the null hypothesis is true, the most natural conclusion is that the null hypothesis probably isn't true. Or alternatively, if the null hypothesis is true, then that sample that we got would be not that unusual. Well, then let's not reject the null hypothesis, because remember, that's our default. And absent other information, that's the thing we think is true. So that's where we're at. We're currently just writing hypotheses, and then we're gonna talk about well, in a little bit, how to determine what really unusual or not that unusual means. There's a statistic we use called the p-value, and we'll learn how to calculate that. Yeah, but in the next video, I'm going to talk about errors, type 1 and type 2 errors. And unfortunately, I'd really love to show you how to do this next, but before I can do that, I have to introduce some terminology in the error section. So yeah, we're going to do that. We're going to do that next. So I'm going to go ahead and end the video here. Stop sharing. I'll end the video here, and the next video will be about errors. It should be relatively short, I think, but we'll see. All right, well, I will go ahead and see you in the next one.